Dear students, today we are going to explore a very interesting and useful concept, the relationship between atomic bond and the physical behavior of materials. You already know this is the periodic table of elements. These elements were created in the universe, most of them formed inside stars, except hydrogen, which was the first element that appeared at the beginning of the universe by itself. The elements are arranged in the periodic table according to their atomic number, which represents the number of protons in the nucleus. The atomic mass depends on the total number of protons and neutrons together. Each element has a different electronegativity. Even though elements are electrically neutral, differences in electronegativity makes them attract or repel each other elements, forming bonds in various ways. We have seen that there are three main types of bonds between elements. The first is covalent bond. When two highly electronegative atoms come together, they cannot easily give or take electrons, so they share electrons to become stable. The second one is ionic bond. When one atom is highly electronegative and the other is weak, the weaker atom donates electrons and the stronger atom accepts them. The donor becomes positively charged and the receiver becomes negatively charged. These opposite charges attract each other, forming an ionic bond. The third one is the metallic bond. When two weakly electronegative atoms come together, both tend to give away electrons. These electrons move freely around the atoms like a sea of electrons, which holds all the positively charged metal atoms together. Now let's go deep into the first type, the covalent bond. A covalent bond forms when two highly electronegative atoms share electrons to achieve a stable electron configuration. In the periodic table, these highly electronegative atoms are found mostly on the right side, especially carbon, nitrogen, oxygen, and fluorine. These are small and light elements, abundant in nature, because such lighter nuclei can be formed even in smaller stars like ours, unlike heavier elements that need large stars to form. That's why our Earth has plenty of carbon, nitrogen, oxygen, fluorine, and silicon, some of the most abundant elements forming covalent bonds around us. Let's see a few examples. Nitrogen and nitrogen. Each nitrogen atom needs 3 electrons. When two nitrogen atoms come together, they share 3 pairs of electrons, forming a triple bond. That's what makes nitrogen gas. Oxygen and oxygen. Each oxygen atom needs 2 electrons. Two oxygens share 2 pairs of electrons, forming O2. Carbon and oxygen. One carbon atom shares 2 electrons with each of the 2 oxygen atoms, forming carbon dioxide. These are all small and stable molecules. Once formed, they hardly react with other elements. Most of these elements are in gas form because these are all small molecules. Our atmosphere is mostly consist of these gases. About 78% are nitrogen, 21% of our atmosphere is oxygen, and roughly 1% is carbon dioxide and other elements. So most gases you see around are covalent compounds except for a few inert gases. But there is one special covalent compound that behaves very differently. That is H2O, water. Here is a simple question. If H2O is such a small molecule, just like N2 and CO2, why is it in liquid form at room temperature instead of a gas? Now let's see why. In a water molecule, one oxygen atom bonds with two hydrogen atoms. Oxygen is highly electronegative, so it pulls the sad electrons towards itself, making the oxygen end slightly negative and the hydrogen ends slightly positive. This makes the molecule polarized, with one side positive and the other side negative. When another water molecule comes close, the positive hydrogen of one molecule is attracted to the negative oxygen of the another molecule. This weak but continuous attraction is called a hydrogen bond. When millions of water molecules form these hydrogen bonds, they hold one another tightly and don't escape easily. That's why water stays liquid at room temperature, even though it's a small molecule. When water is cooled, the molecules lose energy and start arranging neatly in a fixed structure. They become locked in position and cannot move. That's ice. When water is heated, the molecules gain energy, break the hydrogen bond, and move apart rapidly, becoming gas. At room temperature, water flows freely as a liquid. At lower temperature, it becomes solid ice, and when heated, it becomes steam. So, even though H2O is a simple covalent molecule, its molecular arrangement and hydrogen bonding give it a unique behavior. Now, let's move on to one of the most interesting elements, carbon. Carbon is special because it has 4 valence electrons and needs 4 more to become stable. It is small, only 6 protons, but extremely versatile. Carbon can bond with 3 other atoms and still use its fourth bond to attract to another carbon. Once two carbon are linked, each of them still has open valences to connect further. And this can continue endlessly. That's why carbon can form very long chains and combine with hydrogen, oxygen, nitrogen, or even other carbons, creating millions of different compounds. Other elements like oxygen or nitrogen can bond only a few times and stop, but carbon keeps going. When carbon combine with hydrogen, oxygen and nitrogen, it forms protein, the molecules that build our body, muscles and tissues. Without carbon, living organisms would only exist as powder or gas. Carbon also form fat, made of long carbon hydrogen chains ending with oxygen groups. When broken down, this gives us a lot of carbon and hydrogen. When mixed with oxygen, they can release huge amount of energy. That's why fat and oil are energy storing components. Even sugar, which gives instant energy, is made of carbon, hydrogen and oxygen, but with more oxygen, so it reacts faster and releases energy quickly. All living organisms on earth are carbon based, plants, animal and human. If you zoom into wood, you will see it's made of cellulose, a long cross-linked carbon compound. Each long chain is starch, and each small hexagonal in starch is sugar. That's why wood burns, it's made of carbon, oxygen, and hydrogen. Petroleum too comes from ancient living organisms, making it carbon based. From petroleum, we get plastics made of long repeating units and called polymers. Each small unit is a monomer, and many monomers together make a polymer. Even rubber, taken from the rubber tree, is carbon based. If you zoom in, the rubber molecule is a long chain of carbons and hydrogens with a few oxygen at the end. These long chains behave like strings. Imagine a cotton ball where each fiber is a molecule. When you press it, the fiber moves and slides. When released, they return to positions. That's why rubber and plastic can bend and stretch. If you observe a hydraulic press acting on plastic, you can see that it bends and stretches and buckles because these long polymer molecules move relative to each other. All these proteins, fat, sugar, plastic, and rubber. So, how carbon's covalent bonds can form endless variations of materials. Now, having studied the versatility of carbon, let's look at something even more surprising. Did you know that the pencil tip you use to write is also made of pure carbon? Yes, it's called graphite. But what's really amazing is that the same carbon that builds up our body also forms this soft, black, shiny material. If you zoom into graphite, you will see that the carbon atoms are arranged in a two-dimensional hexagonal pattern, something we call a 2D structure. This means it looks like thin sheets of carbon atoms stacked one over another. The surprising fact is that you know very well the carbon has to make 4 bonds. But if you look at graphite closely, each carbon makes only 3 bonds. What about the fourth electron? That's the interesting fact of graphite. The fourth electron is not bonded, it is let free. That's why graphite is the only non metallic conductor because of this fourth electron which is moving free like metals. This is also the same reason why graphite is shiny. These layers of carbon atoms are held together very weakly. So they slide easily. That's why graphite feels smooth and slippery. When you write with your pencil, these thin carbon layers slide off and stick to the paper. That's why you are able to write. Is it that interesting? A soft, smooth black material completely made of carbon? But wait, can you believe there is another form of carbon that's transparent, shining like glass on the hardest material on the earth? You'll be surprised because that too is made of the same pure carbon atoms. Yes, diamond is also made of pure carbon. It may be hard to believe that something as soft and dark as graphite and something as bright and hard as diamond are made of the exact same element, but it's true. The difference lies only in how the atoms are arranged. In diamond, every carbon atom bonds with four other carbon atoms, forming a three-dimensional network. It's not like a single molecule or a long chain, or not even like a seed. It's a solid 3D structure where every carbon is locked tightly in place. This type of arrangement is called a covalent network solid. Because all the carbon atoms are strongly bonded in all directions, it's impossible to move even one atom. If you heat it, the atoms cannot vibrate freely. It cannot even melt. Instead, it burns at extremely high temperature. That's why diamond is so hard. You can use a diamond to cut glass, but nothing can scratch a diamond. So, diamond and graphite are both pure carbons, yet completely different. Graphite is soft, dark, and slippery, while diamond is transparent, bright, and extremely hot. You can never melt diamond in earth, all because of the arrangement of atoms. Having studied the covalent bonds of carbon, nitrogen, oxygen, and fluorine, which are small and abundant in nature, let's look at one more important element, silicon. Silicon is the second most abundant element in Earth's crust and belonging to the same family as carbon, with four valence electrons. So, silicon too can form four covalent bonds. Most of the silicon found in nature exists as silicon oxide, which is what sand, stone, glasses are made of. This shows that silicon, like carbon, can form large, strong structures, but there is a difference. Silicon atoms are much larger than carbon atoms. So, two silicon atoms cannot easily bond together. Their large nuclei repel each other. Hence, silicon prefers to bond covalently with oxygen. At first glance, you might think silicon oxide is a small molecule like carbon dioxide, one silicon in the middle and two oxygen on the sides. But that's not the case. In reality, each silicon atom bonds with four oxygen atoms, each through a single covalent bond. Each oxygen atom in turn bonds with two silicon atoms, forming a three-dimensional covalent network, similar to the structure of diamond. Because of this, silicon oxide forms hard, rigid materials. However, it's brittle. When you press it, it doesn't bend or stretch, it simply breaks. You can observe this with glass under hydraulic press. It cracks instead of bending. Diamond, on the other hand, is even harder because the carbon carbon bond is stronger than the silicon oxygen bond. That's why diamond can cut glasses so easily. Now let's look at another important idea, the crystalline structure. On the right side, we have crystalline solid, where atoms are arranged uniformly and regularly. That's why they are called crystals. Diamond is a perfect example of a crystalline solid. On the left side, we have amorphous solids, where atoms are arranged randomly without a fixed pattern. Glass is an example of amorphous solid. So both diamond and glass are covalent network solids, but one is crystalline and uniform while the other is amorphous and random. This difference gives us completely different physical properties. Now we have explored most of the important covalent bonds around us, from small gas molecules like nitrogen, oxygen, carbon dioxide, to unique compound like water, and to the solids like graphite, diamond, and silicon oxide. We have seen how the types of bond and atomic arrangements decide a material strength, flexibility, and behavior. So remember, the properties of a material do not depend only on what it's made of, but also how its atoms are bonded and arranged. That's the fascinating world of covalent bonds and how they shape everything around us, from the air we breathe to the water we drink, the glass we touch, and even the diamond we admire.